right. Hello. Happy Monday to you all. You guys are doing well. So today the plan is to talk some more about relations, properties of relations that you guys did some reading about, reflexive, symmetric, transitive, and then kind of move into equivalence relations shortly after that. So I think we might start that a little bit today. Don't forget, you've got your homework that is due this evening. Homework 8 is up. I posted that this morning. That is going to be due next Monday. I will collect that and grade it. I won't be able to grade it in time for your exam, which is on Monday, or excuse me, on Wednesday of next week. So I'll put the key up online so that you can check your proofs against them. But yeah, I will grade that work. Yeah, so the plan is to kind of go through equivalence relations, equivalence classes this week, do some review on Monday, and then the exam will be a week from Wednesday. So any questions about that plan before we get started today? Okay, well, hope everybody is hanging in there. Okay, so 3 definitions, 3 properties that are particularly nice for, we'll see are going to be nice for relations to satisfy are reflexive, symmetric, and transitive. So these are defined below. So any questions about those definitions? So then let's kind of consider some of these examples below. So I just want to make sure we're kind of comfortable getting a gist informally of what it means for a relation to satisfy these properties, and then we'll talk about how we can prove them more formally. So for the equality relation, what we'd want to check on the real number. So we have a relation defined on a set. So we need both some rule for the relation as well as a set to go along with that. So for equality, if we're thinking about the reflexive relation, right, we'd want to check to see, is it true that A is equal to A for all A in R, right? And that would be satisfied. And if we wanted to check symmetric, then we'd want to see, okay, if A is equal to B, then is it true that B equals A, right? And that is also true. So that's what we're checking for symmetric. We'll see that sometimes the ordering does matter when you start to think about some of these other relations further down. And then for the transitive property for equality, we would want to check if A is equal to B and B is equal to C, then does it follow that A is equal to C? That would be true here. So the equality relation satisfies all 3 of these properties for a relation. Any questions? Okay, so I am going to just take some polling about some of these, and depending on how these go, I'll probably leave some of them for you guys to think about. But let's think about the not equal to relation. There should be 3 questions in this poll asking you about each of the 3 properties. So not asking for like formal proofs at this point, but just kind of based on your understanding of these properties, do you think that the relation not equal to satisfies some of these properties? Okay, for anybody still thinking, please take another 10 seconds to get your response in. Awesome, thank you. Okay, so here were the results. So if we go by a majority here, at least we had no on reflexive, yes on symmetric, and a no on transitive. So at least the majority of people were right about these. So it is the case that we've got a no here and a no here. And we have a yes for the symmetric one. And if we kind of just do some scratch work on this, what's a counter example for the reflexive property? So in other words, what is an element in this set such that the property for reflexive, oh, let me share these in case you want to see, sorry. Can you guys think of an example? What is a element A that's in the real numbers for which A not equal to A is not true? You can chat it in if you prefer. If you're still thinking about it, I think you're thinking too long and hard about it. Does anyone think of a real number so that A not equal to A would not be true? Yep, 1 works, 2 works, pi works, E works, minus 59 works, right? Any number that you pick, this is going to be the case. But keep in mind, when we're disproving something, we just need to provide 1. When we prove this is true, we're going to have to, that's usually harder, right? We need to prove it's true for everything in that set. The transitive property, right? This one would also not hold here for the same property that we're thinking about. And again, you could probably think about just about any 3 numbers in R. And we see 1 is not equal to 2. 2 is not equal to 3. Sorry, I guess I can't pick just about any 3 numbers here. And then the question is, does that follow? And that does. So this is actually not a good counter example. Does anyone see how we could fix that? Yeah, so that would work. Thank you, Zoe. So if we pick 3 numbers, they don't say anything about these 3 things being distinct. It is true that 1 is not equal to 2, 2 is not equal to 1, So the hypothesis part of that implication is true, but the conclusion, which would be A, should be related to C as well, but that relation is not true. So notice that this property works for almost all three numbers that we pick in R. But it's not true for all. Okay, so just recall that we read these implication statements as for all statements. So what I mean by that is this definition is saying for all A, B, and C, if A is related to B and B is related to C, that should imply this. So if we can find one counterexample, that would disprove it. And so there was a question that says, could we repeat numbers? And there's nothing in this definition that says that A, B, and C need to be distinct numbers. So yes, you can do that. And in fact, you would want to make sure that it holds if A equals B equals C. But that should pretty much follow from up here. But yeah, so this should be true for all pairs, even if some for all A, B, and C, even if some of A, B, and C are the same. Yeah. Okay. Any questions? I'll take answers or questions. I'll take anything these days. Okay, so let's take a look at the next one. And let me relaunch this. And so now we're thinking about the less than or equal to relation on R. And think about which of these properties seem that they would hold for the less than or equal to relation. Okay, so if you're still thinking, I think we got one more person, try and get your answer in. This is not being graded, just getting a pulse check here. Awesome, just in time. Okay, so here were the results. So people were saying that this is reflexive, and this would be reflexive here. Right, and the important thing is we have that inclusive inequality. So it is true, for example, that 3 is less than or equal to 3. So the reflexive property holds. The symmetric property was a little bit more split. So does anyone want to explain why you are correct that this is not symmetric? Does anyone see a counter example for that? Yeah, so thank you. One just came in on the chat to me, so share it with you guys. So if we take 3 and 2, these are two elements in our set. We've got 2 is less than 3, so that checks out, but 3 is not less than 2. So here what we're trying to say is this is going to be reflexive, or excuse me, symmetric if this implies that for all A and B in R. So if I can find one that doesn't work again, that would be a disproof of that. Okay, and for the transitive property, right, that's checking things like this. 2 is less than 3, 3 is less than 4, then does it follow that 2 is less than 4? And so this one actually is going to be satisfied for any 3 pairs of values. And keep in mind, what I'm doing is not a proof right now, right? We would want to prove that more formally. But right now, I just want to make sure that we're getting some sort of intuition about these properties and when we might expect them to work or not work. Any questions? Okay, so there was a question about the inequality one. Sorry, that or the not equal to one. Someone was asking about why is it not reflexive? And so the definition for reflexive says for all elements in the set, it should be true that it is related to itself. So we would ask, well, is 3 related to 3? If we're using this inequality symbol or this relation. And if that were the case, then this would have to be a true statement, right? But we know 3 is equal to 3, so this is false. So therefore, by this inequality relation, 3 is actually not related to itself. Okay, good. Any other questions? If we change this just slightly over here, and I take out the equality over here, how would that affect these properties? Is it going to stay the same, or are we going to have something different? Okay, and relaunch this since good, you guys like polls, so I'll take what I can get. This is great. So here we're thinking about this one right now, and let me just erase my answers. I'm not saying those are right. I was just trying to move down what we had for the less than or equal to one. Now I just took out the equal part. Okay, good. So we got just about everybody in. Perfect. Thank you. And so here were the results on this one. So yeah, so that's right. So here, one change from the one up top is now this is no longer reflexive, right? So what we were checking was, is 3 less than or equal to 3? That checks out. Down here, that is no longer true if we remove that inclusive inequality. It would not affect this property. If A is less than B and B is less than C, then it is going to follow that A is less than C, and it still is not going to be transitive. Okay, any questions?
I do have a question about that symmetric with just the less.
Sorry, I think I missed that. Was there a question? Or maybe my volume's down. Someone, I missed it if someone asked. I thought I heard something. Maybe not.
Yeah, Mitchell was asking a question, but his audio is not working.
Oh,
I think he's typing it in.
for the last one, use 3 and 4. Would it be symmetric? So it is not symmetric. That's right. Sorry. I don't know why I put yes here. I mixed these up. You're right. Thank you, Mitchell. So it's still a no on this. I think I said the right thing, but I wrote them in the wrong place. And that would still be transitive. Yeah, so it is true if A is less than B and B is less than C, A is less than C. So the transitive part holds, but yeah, the symmetric part is definitely not right. Thanks. Okay, so we skipped over the parity one. So remember, same parity means we would say like 3 is related to 5 by this because they're both odd, right? And we would say that 3 is not related to 4 because they have different parity. We would say 4 is related to minus 10 because those are both even numbers. So do you think this parity relation, which of these properties do you think it satisfies? Okay, please take another 10 seconds. Awesome, thank you. So here are the results. So yes, this is a reflexive property because we want to check to see, is it true that a number has the same parity as itself? So that is certainly going to be true. As far as whether or not this is symmetric, so if A has same parity as B, then certainly B has the same parity as A. So that is also a yes. So that was, most people were thinking there. And then we had some, there was some division of opinion here with the transitive property. And so let's think about this. I'll come over here and do some scratch work. So I think this was defined on Z. Yeah. And the question is it transitive? So in other words, what we want to think about, if A and B have the same parity and B and C have the same parity, then what we want to know, does that therefore follow that A and C have the same parity? And so again, we'll get into how we can prove this formally really soon. But for now, we're just kind of thinking about whether that seems reasonable or not. Right, if you think about it, if A is even and B is even, then in order for B to be related to C, we know that B is even. That would have to imply that C is also even. So therefore, A is related to C because they are both even. And we could do a similar argument for odd. So this is a yes for the transitive properties. So that is definitely the more complicated of these properties. So that was some division there. So if you were a little bit unsure, confused about that one, so were others. So let me know if that clears it up or if you still have some questions. It might help other people as well if you share. Okay, so that was a yes and a yes and a yes. So these guys here, so far, they satisfied the, oh, look, all three of these properties are true. The others have not satisfied that. Okay, I don't want to go through every single one of these. Just trying to build some intuition again. So we'll come across some of these in a bit. Let's see. Maybe let's try another one, and then we can see how this is going. So let's try. I'm going to skip over the modular arithmetic one since we'll revisit that one on the next worksheet. But let's think about the divide one, and let's see which of these properties do you think are satisfied here. Okay, take another 10, perfect. Get that in right when I give the warning. Okay, so here were the results here. So we had most people thinking that this is indeed reflexive. And so it is true that for any integer that I pick, that it's going to divide itself, since I can write 7 as 7 times 1, right? So what it means to divide a number means that it is a factor of that number. So every number divides itself. So that is yes. So that was good intuition on that one. Is the relation symmetric? And that's right. for the majority here said no, and that is true because, for example, 2 divides 4, but 4 does not divide 2. And as far as is this transitive, seems like this one has been giving us the most kind of diverse opinion here, since this is has the most moving parts, the transitive property. But if you're ever kind of stuck, I don't think it hurts to just write out an example and see, okay, like 2 divides 4 and 4 divides 20. Would that therefore imply that this should divide that? And if you write out a number of examples, you'll quickly convince yourself that that's true. And you might be thinking, like, when we did one of these other examples, we kind of did one where, like, we picked A, B, and C, and we picked A and C to be the same value, and that like screwed up the transitive property. That wouldn't be an issue here. I could pick 2, 4, and 2 as my integers to check here. And then what it means to be transitive is if 2 divides 4 and 4 divides 2, then it should follow that 2 divides 2. And this statement is in fact true, right? Because this is false here. So this is really not even something to consider. So we would get a contradiction if both of these things are true, but that thing is false. We have the hypothesis is false, so it doesn't even, we don't even care about a conclusion because this is not an example of A related to B and B related to C. Okay, so good. So this one checks out for transitive property. Okay, so any questions about these properties so far? Okay, so I think I'm gonna kind of stop going through these one by one, but I'll put the solutions for the rest of these up when I post it. So it would be good for you to try and go through these on your own. We're going to be sticking with reflexive, transitive, symmetric for the rest of today and tomorrow. So we're not moving past that. If you still have some questions about that, there'll be some time to work through them. Okay, so one thing that's good to note here is, given any set, the total relation. So remember, the total relation means that everything in the Cartesian product of A cross A is in the relation. So maybe we typically call that relation T for total relation. And the empty relation this would be the empty set. Nothing is related to anything else. So this total relation, right, is going to be yes on everything because everything is related to everything else. So we're not going to worry about symmetric, transitive, reflexive, since everything is going to be related to everything else. So this is true. okay, no matter what the set A is. And for the empty relation, we actually have a no NES yes for this one. The reflexive property doesn't hold because, right, each element is not related to anything else, including itself. However, the reflexive, or excuse me, the symmetric and transitive properties would hold, and it's kind of like a vacuously true statement because there's nothing to check. Since when we're checking these properties, we want to see if this is related to that, does it imply this? And if we have an empty relationship, there are none of these to consider, right? So nothing is related. There is no A related to B, so I don't even have to worry about the conclusion. So these conditional statements, the hypothesis is going to be, there's no cases to consider. So that's why those follow. Okay. So can you find a relation on some set A that is reflexive, symmetric, and transitive okay? So yes, a total relation would work for any set A, right? That's going to definitely satisfy all of those properties. And we want to think about what is something that has none of the three properties, or only two of the properties. These are a little bit trickier to think about. So here's what I'm going to do. I'm going to just split us up into discussion room. And what I'd like us to do, maybe let's consider the same set. So let's consider the set A, which is 1, 2, 3, 4. And what I'd like to do, what I'd like you guys to think about is write out the relation, right, which again is going to be a subset of A cross A. That's going to satisfy reflexive and symmetric. And let me just add here. Okay, but it's not transitive. So just to be clear, right, if we want this to be reflexive, then what other elements should definitely be in this relation? So I'm going to say that 1 is related to 1. What else? So right now, I'm just going to try and focus on the reflexive part. That's right. So yeah, and then we'll think about symmetric and the transitive part. So as far as the reflexive is concerned, sorry, I forgot my 4, 4. In fact, that would also, if I just stopped here, that would satisfy all of those properties. The transitive and the reflexive property, there would be really nothing to check for those. So what I want you guys to think about are what else would we need to include so that it's symmetric but not transitive. And if you figure that one out, then try and think about 3. But any questions before I break us up into different groups? All right, welcome back, everyone. Okay, so let's compare notes about what was going on in these rooms. So I'll summarize what kind of the thought process, and feel free to chime in, room, if I summarize something wrong. But we kind of started by thinking about adding in some things like this, a bunch of these pairs. So it makes sense that if I want this to be symmetric and I put in 1, 2, I need to be sure that I include 2, 1, right? Or else we're going to violate the symmetric 1. And so they said, okay, let's put 1, 3 in. That means we need to have 3, 1 in here. Let's put 1, 4 in, and then we need to have 4, 1 in here. And the problem with this is that it satisfied everything, all 3 properties. So I don't know, what were you guys able to come up with an example in the other breakout room?
We had what you wrote right now.
Okay. And then did you tweak this, or this is kind of where you guys were at when we came back together?
That's where we were analyzing these sets.
Okay. Yeah, and so if you try to map out all of these properties, right, we have too many relations in here. So this actually would also satisfy the transitive properties. So we kind of talked about, if we're adding things in, it seems like we might be increasing our odds of satisfying these more properties. If we take some of these relations out, maybe we'll violate some. So we thought about taking out, trying to remember which way we did it. I think we took out this one, possibly. And we said, okay, now let's take a look at things. So it's still reflexive. It's still symmetric. And now let's think about if it's transitive. And we want to be careful because we could consider 1, 2, and 1 as elements in our set A, because remember, we can repeat things. And here we do have that 1 is related to 2 and 2 is related to 1. So this is our A is related to B, B is related to C, just our A and C are the same in this case. And it does follow that 1 is related to 1. So it does follow in this case that that property holds. But you want to be careful again that just because it works for some doesn't mean it's transitive, right? We need to check that it works for all such things. So a counterexample here would be like 1 is related to 2. That's not right. We have 2 is related to 1 over here. And then we have 1 is related to 4 from this one. Right, but 2 is not related to 4. So it is not transitive. So kind of, one thing to keep in mind here, if you're thinking about like what is the strategy that I can do here? Well, okay, I need to, what we did is we made sure first that we made it reflexive. And then we started adding some stuff to the set, making sure that we're satisfying the symmetric property. And then we looked at the transitive property. And if the transitive property worked, then we thought about what are some things that we could pair out of this set so that the transitive property would no longer work. Okay, so let's see, so sorry, we did this one, we talked about the total relation. If I consider the same set here, then let's consider what's a relation that I can define on this set that is going to not satisfy any of those three properties?
What if your set were to just have one element?
What element would you like?
Let's do one.
Sorry? So if I add like an element like this is not reflexive. Right, since, for example, we don't have 2 related to 2. This is symmetric since 1 is related to 1, which is related to 1, which is, well, that's all we need for symmetry. Whoops. And it kind of trivially satisfies, well, I guess we've already failed here, right? Because this does satisfy one of those properties at least. It does satisfy the transitive property as well. So I like this idea. Let's try an element. Maybe 1, 1 didn't work. Any other thoughts? So these pairs that we write, for example, I couldn't put one empty set because empty set is not an element of this set over here. So my ordered pairs have to be something, one of these 4 numbers, comma, one of these four numbers. Okay, so here's a suggestion. Let's try 1, 4. Reflexive does not work for any of them. It is now no longer symmetric since we have 1 is related to 4. But 4 is not related to 1. Okay, however, this is transitive because we don't have any such A, B, B, C's to consider. There's only one element here. So I do have that 1 is related to 4. And to complete this, right, the only other thing to consider is, well, is 4 related to something else? And we can see here, 4 is not related to anything. So this transitive property is kind of like vacuously true. So we have right now the fact that it's not reflexive, great. It's not symmetric, great, but it is transitive. So any thoughts about what we can add to this set to violate it? So that, for example, I have 1 is related to 4, maybe 4 related to something, and then we'll kind of strike out. So there was a suggestion to add 4, 3, probably 4, comma, almost anything, or a couple of options would work here. So if I put a 4 and 3, if I relate 4 to 3, then in order for this to be transitive, we would say, okay, that and that are satisfied by my relation R. But what we don't have, in order for the transitive property to hold, we would need to have 1 related to 3. So I'll kind of leave it for you guys to play around with this. I think this is a really good way to get a good intuition about these properties, is to try and come up with some examples or counter examples of things that satisfy some but not other. So yeah, I would say try and think about, can I find one which is reflexive and transitive, but not symmetric, and so on. Okay, any questions?
I have a quick question.
Sure.
Can we go back to number 1 real quick?
Mhm.
For, yeah, for that one, it's like, it's reflexive for 1, 1, 2, 2, 3, 3, and 4, 4. But like starting at 1, 2, even though that particular like pair is not reflexive, does the whole thing need to be reflexive, I guess, is my question. Like, do we only need to find the pairs that are reflexive, then include it, and then it's all good, and we don't have to worry about that?
Do you mind saying that again? I just want to make sure I understand.
Yeah, so like, for example, like, so far we have like 1, 1, 2, 2, 3, 3, and 4, 4, which are all reflexive, but starting like the pairs after that, like 1, 2, 1, 4, those pairs are not reflexive. So is that all right? Or I guess like, do we come up with pairs that I don't I don't know how to explain it, but like everything following like 4, 4 is not reflexive.
Yes. So in order for a relation to be reflexive, it means for all elements in the set A, we need that A is related to A. So it doesn't say that if we have some other relation that A is related to B and B is the same as A, then this violates reflexive. That doesn't violate the fact that this is reflexive if we include additional things in there. All we're saying is that if this is going to be reflexive for everything in A, we need to have A related to A. So for this element, we have 1 related to 1, 2 related to 2, 3 to 3, 4 to 4. That satisfies reflexive. If I don't have one of those, it's not reflexive. But if I have all 4 of those, no matter what else I add to this set, it's definitely going to be reflexive.
Oh, I see. Okay, sounds good.
Okay, anything else? Okay, so I'm just chatting in the next worksheet, and if you don't have that downloaded, so we'll start this a little bit right now, and we'll finish it up next time. So we've been working with these properties: reflexive, symmetric, transitive. So we say that a relation is an equivalence relation if it satisfies all 3 of these things. And what I'll just say is, well, like, it might seem weird, like, why did you pick these 3 properties? Why not less properties, or why not consider additional properties? And we'll see that if a relation satisfies this property, it's going to give us a nice way to partition the original set into some nice well-defined things that we call equivalence classes. But we'll see that next time. So what I want to just think about right now is, how could we do a more formal proof? For example, here's some relation. How can I prove that a relation is an equivalence relation? And so maybe I just want to walk through one example before we go for today, just so you have a sense for the feel of this, and then we can kind of talk about these techniques next time and practice them. So yeah, so let me do one that's not on this sheet, actually. So let's say we want to prove so if I want to prove that some relation defined on some set, and this is the real numbers now, is an equivalence relation, then when we do these proofs, we're going to have three things here. And this is one of these nice proofs where you should be kind of labeling out these parts. So there's going to be a part of the proof where we want to check for the reflexive property. There's going to be a part of the proof where we check for the symmetric property. And there's going to be a part of the proof where we prove the transitive property. So just to kind of keep in mind, what are our what sort of statements we're working with? These are all conditional statements. That means we might use direct proof, we might use contrapositive proof, we might use proof by contradiction on these. And the reflexive statement is a for all statement, which we can think of as a conditional statement as well. Right, so these are each of these statements written out as a conditional statement. And again, just be clear that like when we read conditional statements, we do interpret them as for all. So just because I see that one such pair works, that doesn't mean it's transitive. We need to show that this works for all such things that satisfy the hypothesis. So if we were trying to prove, say, the equality one, I realize that will probably be the one piece that we can get in today, then we could do this, in any one of these proof methods. Let's try like direct proof, since that seems to be the logically speaking, the most clear proof technique. Then we start with assuming this is true, and then we try and show that the conclusion is true. So we would just say, let A be an element of R. Okay, and this is just like a very trivial relation here. They're not going to all be so easy, but that's the gist, right? I mean, I just needed one sentence here, but like for any real number, we know it's equal to itself. But that's the type of thing that we would need to check. So yeah, we'll work on these proofs next time, showing that things are equivalence relations, and then see why it's nice having these three properties, and what sort of partitions we might get for these sets. Okay, so for Wednesday, you guys have another reading quiz that's going to be kind of relating to this. And I think that I didn't put up a video just because I think that it is, the book does a good job of explaining it. So I think you should be able to read the book and go through the quiz without too much trouble. But if you do have any questions about that or the homework, Lindsay has office hours later today, and I've got some office hours tomorrow. Do you have office hours tomorrow too, Lindsay, or no? Okay.
No, just today from 1 to 2.
Okay. Yeah, so Lindsay's 1 to 2 today. I've got office hours tomorrow from 1:30 to 2:30. Otherwise, have a nice afternoon, everybody, and I will see you all on Wednesday.